Okay, so now we turn our attention to applying Newton's laws to an object moving up or down a ramp. Now, a ramp, sometimes called an inclined plane, is one of 6 simple machines. And so simple machines are something that typically covered in maybe an introductory physics course or maybe in earlier grades, but there's really 6 of them. The wheel and axle, the wedge, the lever, the inclined plane, the pulley, and the screw. Well, the inclined plane is very useful in the way that it sort of helps us work, do things against a gravitational force much easier than just doing things without a ramp. And you'll see how that pans out in this slide. So the title of this slide, how does the normal force respond when an object is on a ramp? Well, this is not just about the normal force. And so I wrote that line up there thinking that I wanted to make sure you realize the normal force is a responsive force. It's something that responds to the environment. It is not always equal to the weight of the object. And so sometimes we have to consider changes to the normal force based on things like motion along a ramp and so forth. Now, let's take a look at a simple case of an object just sitting on a flat table. We know that the Earth pulls on an object with a force equal to the weight force, which we've calculated as m times g. Now, we also know that the table would exert, in this case, a normal force we've been calling n. We call it again normal because it's perpendicular to the surface. And we know that if the object is not changing its state of motion, that the normal force and the weight force would be exactly equal. Now, that's wonderful for description of motion along a flat table, where our x and y coordinate axes are usually chosen the way that we normally write them in a math setting is sort of in a horizontal and vertical fashion. That makes sense for that kind of motion. When we start to look at an object along a ramp, though, then we oftentimes will rotate the coordinate system so that the motion that we have, the object moving up or down the incline, right, so either up or down, is along one direction of my coordinate system. So we often change the coordinate system so that it is aligned with the inclined plane. So y is usually perpendicular and pointed up from the incline. X, sometimes we call the x direction positive down. Sometimes we call the x direction positive in the opposite direction. Really depends on which way it's moving. Oftentimes we choose the positive direction to be the way that we're moving. But regardless, it is going to be parallel to the plane surface. Now, let's take a look at that weight. Remember, the weight is always straight down, and its size is always calculated by m times g. So regardless of where I am and what kind of ramp I'm using, the weight force would always be m times g. Now, I'm drawing this as a dashed line because we're going to change that weight force into 2 components. That weight force now would need to be changed into a component that lies along my y-axis. I'm going to call that w in my new y direction. And also a weight force that sort of acts parallel to the ramp surface, which would be the projection of the weight onto my new x-axis. I'm going to call that w sub x. Okay, so this is like a vector resolution problem. It's wonderful that we've rotated our coordinate system so that the motion is only 1D. Makes it far easier to describe it. But when we deal now with a force that's in a direction that has both an x and a y component, it's easiest if we sort of break that into its 2 components. Okay, so now our weight force acts completely in the y, and there's a different distinct weight force that acts completely in the x. Okay, so that allows us to eliminate w and replace it with these 2 things. Now, for vectors, I can take a vector and I can relocate it anywhere that I want, provided I don't change its length and I don't change the direction that it's pointing. So even though we would typically draw an FBD like so, in order for us to figure out how w sub x and w sub y relate to the value of w, I'm going to move that vector, w sub x, I'm going to move it down here so that it's tail to tip with w sub y. So I'm just going to simply slide that vector. So for the time being, I'm just going to get rid of that, place it down here. Now I want to zoom in here a little bit so it's easier for us to see that. Whenever we resolve a vector into components, the components are chosen so that they're perpendicular. So we have a nice little right angle there. That angle, let's just call it theta, the angle that the ramp makes with the horizontal, can be shown to be the same angle as that there. That angle theta is the same as the angle of the ramp. Now I'm going to save the proof, which is largely geometry based. Save that for a different video. But if you're interested in trying to show that, that might be a worthy exercise for you. Regardless, what I want to do is I want to try to figure out now how the weight force acting along the incline, W sub x, is related to the actual weight and that angle. Now, because it's a right triangle here, I'm allowed to use things like sines, cosines, and tangents. So I'm going to use the memory aid SOHCAHTOA to help me figure out these relationships. I see that W sub x, the weight force acting along the incline, is the opposite side to that angle theta. I know the hypotenuse, the weight is the hypotenuse, so I really know the hypotenuse, and I'm looking for the opposite side to that, so I'm going to use the sine function. The sine is defined as a ratio of opposite to hypotenuse, so if I'm looking for that opposite side, it would be the weight of the object multiplied by the sine of the angle of that ramp. Okay, so there is one of our relationships that we will be able to use for how the weight is sort of changed to be aligned with our x and y coordinate systems. Similarly, I can take W sub y and make it be W times the cosine of theta. So a little bit of trigonometric review there. Okay, so these two equations are ways for us to deal with the weight now acting along an inclined plane. Now let's look at the normal force. The normal force is, remember, it's something that sort of responds to the environment. So if the environment changes somewhat, for example, from this example, we no longer have the crate on a level surface. Now we have it on an inclined plane. Even though the weight stays the same, right? We still have the same weight. We see that the normal force does change. The normal force is always perpendicular to the surface. Okay, so that is now perpendicular to the surface, but notice it's also smaller now than the actual weight. The normal force sort of responds to being on a ramp. The normal force becomes smaller than the actual weight. It's only equal to the weight force acting into the plane. Okay. Now, let's take a look at that example applied to a steeper ramp. Let's go ahead and draw the weight force and the normal force for this particular system over here. So let's again start with a coordinate system that's rotated. So I'll call that y. I'll call this direction x. And that weight force, again, always the same value for w, but I'm going to resolve it into its components that are now along my new chosen coordinate system. I see that the weight force acting into the plane is now quite a bit smaller than it was before. And the weight force acting down the plane is actually quite a bit larger. So W sub x becomes larger. I'm going to go ahead and draw that up here tail to tail the way that we normally do for FBDs. Now, the normal force, which is also acting on this object, is becoming quite a bit smaller now. N, the normal force, is reduced substantially from where it was over here simply because the inclined plane is at an angle now to the horizontal. So that force and this force would be equal. Let's talk about one of the reasons the inclined plane is so valuable. When we take an object and we try to move it along an inclined plane, let's say I'm trying to push the object up the inclined plane. Well, instead of having to lift it straight upward and work against the entire weight by exerting some applied force that's equal to all of that weight, I'm only going to have to exert a force that's just a small sliver of that weight. It's just the force acting down the plane that I would have to exert in order to move that thing up. I can do this much more easily than having to lift with all of that force. So inclined planes actually help sort of reduce the amount of force that I need to actually change the location of an object by lifting it. I don't have to lift it with all of the weight force. I can actually push it with a much smaller force. Now, if I'm going the other way and I say I'm going to let this object slide down the ramp, instead of using all of the weight force to accelerate it, Right here, it would be accelerating at a very large value. As a matter of fact, you probably know what that value is. The acceleration would be all of the acceleration due to gravity. Well, here, I'm only going to get a fraction of the acceleration because I'm only using a portion of gravity. So the effect of gravity will also be sort of slowed. And so here it'd be slowed even more simply because I was a much smaller angle. Here, I would still get quite the acceleration, but far less than if I were just having it fall straight down. Now, those are considerations for weight and normal force along my new coordinate system. Let's go ahead and just fill in some of these blanks down here. We see that the steeper the incline, the smaller the normal force will be. The normal force would be equal to the weight multiplied by the cosine of the ramp's angle. That's provided there's no other external forces acting on the block. Further, we see that there is a component of the weight force that acts parallel to the surface. This force is called W sub x. It's the weight multiplied by the sine of the ramp's angle. That's the component that accelerates the block down the incline. Gravity is, in a sense here, it's sort of diluted. It sort of happens, the effect of gravity happens more slowly when we consider motion along an inclined plane. The analogy I like to use is if you have to take medicine, maybe when you're a child, and you have to take a full teaspoon of some medicine that tastes horrible, if you take that medicine and sort of dilute it by putting it into a cup of your favorite drink, maybe milk or something along those lines, you can drink the entire cup of milk and get the entire contents of your medicine much more slowly than if you were to take it all at once. What an inclined plane does is it sort of dilutes how quickly gravity can sort of change the motion of an object. We still get the exact same effect of gravity. It just happens more slowly. Said another way, if I were to look at the speed on impact, the velocity down here, v final, that velocity, if I let it fall this entire distance here, the velocity that it acquires would be exactly the same as if it got down here. Right? It would get to the same velocity, v final. It would just do so at a much slower rate. So what the inclined plane does is it dilutes the rate at which gravity acts. It just it doesn't change the overall effect.